Okay, our last section. Pretty exciting, 14.5. So a short version of this, something that we need to do for people that, again, aren't required to take Calc 3, not so lucky ducks, is the chain rule and how you do that for partial derivatives. Okay, it's actually not too bad. How many of you have taken probability and statistics and done the law of total probability? Remember that one, where you make like the cool tree diagram? Okay, well, you get to make a cool tree diagram here. It's something I suggest because it makes our formula for the chain rule. So we diagram something out, and then we'll be able to know what to do. And of course, involves partial derivatives. So first example is not going to be how we're going to actually do this, but just to speak to it for a minute. We have w equals x squared y minus y squared, where x equals sine t and y equals e to the t, find dw over dt. And so there's a way to avoid using the chain rule, which isn't always going to work, but you could do it. So we're going to learn the chain rule. The first case is one where we have a function in terms of two variables, and each of those are a function of some parameter t. So this is actually kind of like a parametric deal, parametric equation. So notice here that what the derivative overall is, first of all, we don't have that partial notation, because the idea here, let me show you the cool diagram. You guys see that in the bottom right? The yellow and green highlighted. So what's going on here is, because z depends on, okay, that's for the other problem, so it's a little confusing, but, oh, it's right here. Sorry, right here. This is my little tree. So notice how z depends on x and y, but both x and y depend on t. So it's kind of like x and y are just gatekeepers to get to t, and z is really a function of t. So that's why when you find the derivative of z with respect to t, it's not a partial, because really, when you do the chain rule in that context, you are just finding the derivative of z with respect to t. And it just boils down to being dependent on t. Alright, so what is the chain rule for this case? Well, some of you might remember the chain rule when it was written in Leibniz notation was actually very much like this. Maybe not. But we take the derivative overall, so the partial derivative with respect to x, because it is dependent on y there, and then you just multiply by the derivative of x with respect to t, where the x here is sort of like the g of x, or the inner function, when we have a composite function. So pretty much that follows from what we learned in Calc 1 with the chain rule, but the difference here is we also have to take care of the y component, which we just do the same thing with respect to y. It doesn't actually happen, but you can kind of think of the y's canceling, and you'd have dz over dt there, right? And then you have the x component from over here, and you add them. And so once you find the change of z with respect to t in the two components, you just add them. And I mentioned the law of total probability from Prob and Stats because that's pretty much what the law of total probability is too. You find the probability for kind of like each component, and then you add them up at the end, and that's the total probability. Alright, so anyway, this is a special case because we're going to expand off of this and have it so that it's actually partial derivatives dependent on more than one variable in the independent sense. It's not just going to be t, it'd be like t and theta or something. So we'll ramp this up pretty quickly, but let's do an example now where we're going to use this. So this one, theoretically, we can avoid the chain, but most of this is going to be having the chain rule required, so we'll just kind of practice it in that sense. So first thing here is our tree, is our function w is at the top of our tree, and then it depends on x and y. And then we're told separately that x is a function of t and y is a function of t. Well, actually, there's more information about that, but at the very beginning, that's all you want to get out of it. And so you can make your tree where w is dependent on x and y, which x and y are like intermediate variables, and then both of those depend on t. So then, writing out your equation for the chain rule is going to be following the path from w and to x, which is in yellow up there, and you're going to find the derivative along that route. So that's going to be the partial of w with respect to x. And then to finish it off, you're going to multiply by the next leg, which is the x to t derivative of x with respect to t. And then the next branch, you add that, is going to be the derivative partial with respect to y of w, and then you follow y to t in green to take the times the derivative of y with respect to t. Law of total probability is the same operations, multiplication and then addition, branches together. So I'm not required to remember that or know that, but just it's useful if you have had it. Alright, so that's what we have. The first thing here I'm going to do is I need to find these partials. So dw over dx. Look at the function w and let's take the derivative of that with respect to x, which means y is going to be held constant. So what we're going to have for the first term is going to be the derivative of x squared, which is 2x, times y like a constant. So 2xy. And then what's the derivative of minus y squared with respect to x? Just 0, right? So for del w del over del x, we get just 2xy. Okay, next thing, dx over dt. So I got another function for x, it's sine t. I'm just taking the derivative of that with respect to t. So what's that? It's just cosine t. Moving on, plus, now we're going to take the derivative of w with respect to y. So doing that, go back to our w function, we got two y terms. So derivative of x squared y with respect to y is what, folks? X squared minus 2y. Very good. And thank you for speaking up so I could hear it over the muffs. Alright, finally, what is the derivative of y with respect to t? It's just what? It's just e to the t. So look at our answer there. It's really hodgepodge. I mean, that's the answer, and we're only asked to find, we're asked to find dw dt. So in a sense, we're kind of done, but if we can, this derivative is supposed to depend on t. And what else do we got in there? We got an x and a y in there. Is it possible to write this with respect to t? It is, because you can plug in the functions for x and y. On the right hand side they depend on t, right? So you just plug those in. So we're going to sub in, it's kind of our last step here, the x and y. So it's in terms of t. So what we have instead of 2xy is going to be 2 times sine t times e to the t. Throw some parentheses in there for clarity. And then that's times cosine t. So it ends up looking kind of a lot worse here. X squared is going to be replaced by sine t squared minus 2y. We're going to get minus 2 e to the t, and then that's times e to the t. So we're just going to simplify that a bit, and we'll call it a day on that one. So we have 2 e to the t sine t cosine t, and don't worry about trying to use identities to make that better. And then I'm just going to distribute my e to the t, so I'm going to have plus e to the t sine squared minus 2 e to the 2t. Alright, any questions on that one? Alright, moving on to the general chain rule. Okay, lots of notation here because we're doing it in general. Suppose that u is the differentiable function of n variables, x sub 1, x sub 2, up to x sub n. And those are like their intermediate variables, like the x's and y's we had before. and each x sub j is a differentiable function of the m variables, t sub 1, t sub 2, etc. up to t sub m, where those are the independent variables, sort of like the t we had in the last example, but it could be like some other additional variables there, like theta or whatever. Then u is a function of t sub 1 up through t sub n, and here's our general chain rule. So here's where making the tree, I think, is just a better way instead of memorizing that or something. It's a little overwhelming. So the idea here is make a tree of your overall dependent variable. In this case, it was defined as u. And then it said, well, then that depends on x sub 1 and x sub 2, etc. up to x sub n, and then those x's depend on t sub 1, t sub 2, up to t sub n. So here's the general tree. Yours will be more specific than this, but the general idea is if we want to find the partial derivative of u with respect to, let's say, t sub 2 is what I have here, but it could be t sub 1 or some other t, then you just follow the path down and you're going to take derivatives along each path, defined by where you start and finish. So the first derivative is going to be the partial with respect to u of u with respect to x sub 1. So see how that's what's the first thing in yellow there? And then completing that yellow path, you take the path from x sub 1 to t sub 2, let's say, finding the partial derivative of u with respect to t sub 2. And so that would be the derivative or partial, in this case, of x sub 1 with respect to t sub 2. So that's the yellow. Plus the green path. Similar type of thing going on there. And then you do that for as many paths as you have to t sub 2. So I think that's a much better way than somehow trying to make sense out of the general chain rule. So we have time to get a start on that, which is good. Find the partial of z with respect to s and the partial of z with respect to t for z is equal to e to the 2r times sine 3 theta. And we're also given r is equal to st minus t squared, and theta is equal to the square root of s squared plus t squared. Alright, make the tree. So you're asked to find the partial with respect to what's going to be the dependent variable, or z, the top of your tree. Okay, z is the star of the Christmas tree here. And so that is the part that is the top of the partial derivative, okay? So z goes on top. And then see what z depends on. Z depends on r and theta, right? Okay, those are going to be your intermediate variables. They're like our stepping stones to the independent ones. So r and theta become nodes on our branch here. And then notice that each of r and theta depend on s and t. They got s and t in them. So they will have little branches coming from them that end at s and t. So one at a time, let's find the partial of z with respect to s. So that means we're going to follow which color path? The yellow one or the green one, guys? The derivative of z with respect to s. Which one? Yellow. Okay, follow the yellow path. And so we're going to take dz over dr times dr over ds plus the other branch that goes to s. So that's what's written there. And that's what we need to do. So now we have to go find a whole bunch of derivatives to plug in there. We don't have time to also dz over dt, so I'm just going to skip that part for now. And go down to finding the partial derivatives so we can plug in to our dz over ds, which, why did I do that first? Okay, whatever. Okay, we're going to... Oh yeah, I did do it first. So many partials, hard to keep track. Okay, so I wrote down the functions again here because they're off the page. dz over dr. So look at that function and identify where the r is. There's just one, it's in the exponent of the e thing. And so then we don't really care about the sine of 3 theta, thinking it's fancy, because it's just a constant temporarily, right? So focus on e to the 2r. What's the derivative of e to the 2r? Use the chain rule. on, you guys. E to the 2r with respect to r. What's the derivative? It's 2 times e to the 2r, because you use the chain rule there, right? 2r is the inner function. Derivative of the outside is e to the original function 2r, but then you have to take the derivative of 2r and times it. So it's 2 e to the 2r times the sine of 3 theta. Okay, so we're going to write that down as side work, and then we'll put it all together. So 2 e to the 2r sine of theta. Just kidding, 3 theta. That's what we had there. Okay, so some other things we need to find is, since we're on, doesn't matter what order you do these, but I'm going to find the partial derivative of z with respect to theta, because I'm just kind of focused on that equation right now. So here we have sine of 3 theta, that's the theta, and the e to the 2r is a constant multiple rule. So what's the derivative of sine of 3 theta? Cosine of 3 theta times what as a byproduct? Chain rule. 3, right? Derivative of 3 theta with respect to theta is 3. Okay, so we're going to have 3 e to the 2r, that's part of the constant, and then we're going to have cosine of 3 theta. Alright. Eventually we're going to have to sub in with our s and our t in there. So just doing that here, you could do it later, then it looks complicated. R becomes st minus t squared. Theta becomes the square root of s squared plus t squared. Man, so these look kind of bad. And then plugging in dz over d theta with respect to st. 3 times e to the 2 times st minus t squared times cosine of 3 root s squared plus t squared. So those are just the partials that were the leading things here, dz over dr and dz over d theta. You need to find the dr over dt and the d theta over dt. Fortunately, they're pretty easy. Look at the r function, and holding the s constant, all we get there is what? So the s is, oh wait, the s is a variable and the t is the, s is a variable. So st, that would be just what? T. And then the derivative of t squared is 0 with respect to s. Okay, we ended at an awkward place. So, but we'll just do that. I'm actually going to continue the recording for my first class. So if you want to stick around, I think I have time to not interrupt the next class too. But the rest of you have to leave, that's okay. We'll review on Wednesday. So taking the derivative with respect to of theta with respect to s, bring down the 1/2, original inside. New power is negative 1/2. Chain rule, take the derivative of s squared plus t squared, and you just get 2s. So subbing in, we have a mess. Our original derivative that we found up above with respect to s and t, plug those in. We had this following junk. So much stuff. And then we just had the t from the partial of r with respect to s. Okay, moving on to the next part. The derivative of z with respect to theta, that partial. Writing that down, that's most of the writing here. And then finally we have in our simplified form, we could cancel the 2's in the 1/2 there. Put the s on top and the root down low. It looks tempting to cancel those roots, but notice that that one is locked up in the cosine, so that's not something you should do. And that's that answer. So we still have the partial of z with respect to theta, or just kidding, with respect to t to do. But that's it for this recording.